Hey guys, how's it going? I got a little setup here. I got a little whiteboard that I can do some problems on. And a couple of you guys have actually already emailed in and asked for a sample problem involving work because you're still struggling with the homework. I haven't kind of looked at those yet, but I wanted to give you guys obviously some more time if you needed to go back and finish those problems, especially 3 and 4. So we'll talk about work a little bit this morning, and then I'll do one practice problem for you to hopefully to help you out. Okay. So the first thing, the two big ideas that we're talking about now are these ideas of work and energy. Energy, think of energy as the stuff that makes things go. And so when I look at moving objects, those objects have energy. And then sometimes we can store energy in objects that maybe aren't moving now, but that could eventually move. Like if I take a slingshot or a rubber band and pull it back, and I can tell as soon as I let that rubber band go, it's going to go flying forward. So there's some stored energy in that rubber band. Or when I hold an object really high off the ground that I'm about to drop it, there's stored energy because gravity is going to accelerate that thing downward. It's going to land, crush toes, crush skulls, things like that. And then obviously you have moving objects. So energy is the stuff that makes things move. Now work is the idea of work is measured as our ability to add energy, give an object more energy, or in some cases take an energy away. Okay. So when we talk about work, we're talking about things that increase the amount of energy that an object or a system has, or work actually decreases the amount of energy that an object or a system has. Okay. And the formula for work is as follows. Work, right? Hopefully we can see that. Let me try and erase. This will be a work in progress, so bear with me. I'm not going to go back and remake videos, but we're just going to kind of go with it the way we have and see what works and what doesn't, adjust from there. Work is equal to the force times the distance, all right? Have a great nap, Ellie. I'll see you soon, okay? Love you. And something else that gets thrown on this at times is this angle, cosine of theta. I don't throw that on my formulas. I just tend to work my formulas this way. I do add a really important thing on here. So I put a little parallel symbol. And what that tells me is that when I'm looking at work done by a force, I can only care and look at forces that are in the same or parallel direction as the object moves. So if an object is moving this way, only up and down forces can do work. If an object's moving that way, only left and right forces can do work. If an object's moving at an angle, then only forces in that direction can do work. Okay? So here's a sample problem that we're going to do. Okay, it says a force of 100 newtons. I'm going to erase this so we can start this problem. And this problem should be a great help if you're working and having a hard time with like question 3 on the homework or question 4. A force of 100 newtons is applied to pull an object down a surface that's inclined 9 degrees. So we have this incline, right? And we have an object that's being pulled down the incline. So we're going to throw an applied force on there in that direction. Do we see that? Okay. It says, let's see. So pull down a 9-degree incline. The object has a mass of 20 kilograms. Probably going to need that information, so we'll write it down. And it's pulled a distance of 2.4 meters. So this length that we're traveling is 2.4 meters down the incline. All right. And the coefficient of friction, mu, is 0.15. All right, beautiful. Now it wants to know the work done by each force acting on the object. So first off, I got to get all the forces. We have Fg is this way. We're going to have frictional force back up the ramp. And we're going to have a normal force in that direction. Okay? And I'm going to go ahead and put our components on there. We have Fgy and Fgx. Okay? Now, to me, the approach for a problem like this is if we just find all the forces using principles and ideas we already know, and then we look at the work equation to kind of figure out the work for each one. Sound good? So let's do that. Let's start off by finding the weight. So the weight, Fg, is equal to mass times gravity. I'm going to need my calculator here. We're looking at 20 times 9.81. So we're looking at 196.2 newtons. Okay? Then we have to find the components for that. We have to find FGX and FGY. FGX is our sine component and FGY is our cosine component. So 196.2 times the sine of 9 degrees is 30.7, we'll say. My daughter might interrupt this presentation at some point, but that's okay. And then 20 times, 196.2 times the cosine of 9 is 193.8. Mom's calling you, sweetie. Time to head up for a nap, okay? See you later. Okay, so we have FGX and we have FGY. Next up, let's solve for things like the frictional force, the normal force, the applied force. We know that Fn, when we sum the forces in the y direction, those forces have to equal 0 because we're not accelerating this way. All right? So we have Fn minus FGY is equal to 0. That means Fn is going to be equal to 193.8 newtons. We got that done, okay? This applied force is 100 newtons, by the way. 100 newtons. We have to find the frictional force. Well, the frictional force we know is equal to mu times the normal force, right? So we're looking at 0.15 times a normal force of 193.8. And we get FF is equal to, let's check. I'm looking at 29.1. Okay, so in terms of all the forces on my free body diagram, we have the normal force identified, we have the friction force identified, we have Fagux-Fagui, and we have FA. Okay, and obviously depending on the problem, you might be given information about an acceleration, so you might not be able to solve for everything the way we did, but it's the same process. It's just another force problem. Now, when it comes to work, okay, the way we figure out the work done by these forces is the formula we wrote up before. I'm going to do it in a different color so we can see it nice and bold. It is work is equal to force times the distance. Can you see that okay? Hopefully. Maybe we'll go darker. We'll go green for the rest of it. Now, again, the caveat to that is we only look at parallel forces. So when I look at my object, I see that we're moving this way down our incline. Well, right off the bat, I can look at some forces and say, wait a minute, FGY is not parallel, it's perpendicular. So FGY is a force that can't do or won't do any work. It's not going to give the object more energy or take energy away from the object. The same is true for the normal force. It's perpendicular to the way we're moving, so it's not going to do any work. So the only three forces that are going to do work are FGX, FF, and FA. And the videos you guys watched talked about the sign. If the force is in the same direction as the motion, like the applied force is, then it's going to add energy into the system. We say it does positive work. If the force is opposite the direction of the motion, like friction is, then it's going to actually take energy out, and we say that does negative work. So we have a positive work for FGX, a positive for FA, and a positive for FF. All right, and we're just going to go through this formula. So for FF, we know friction is 29.1. So 29.1 times our distance of 2.4 is 69.8. So we know that friction, the work done by the force of friction, is equal to negative 69.8 joules. Okay? And then the work done by the applied force is going to be 100 times 2.4, so that's 240, right, joules? And that's going to be a positive. And the work done by FGX is equal to 30.7 times 2.4. So we're looking at 73.7 joules. Okay? And so that is the work done by each of those forces we're looking at. Hopefully this video kind of helps with you guys kind of process through how to do these work problems. Again, treat it like a force problem where we do everything we know how to do in terms of summing forces, setting them equal to F equals ma, solving using the funnest formula of physics, Fagux and Fagis, facts and phase, do all that stuff and find every force on your free body diagram first. And then once you do that, start looking at, hey, let's identify whether or not these forces contribute to adding or taking away energy. And then what is that amount of energy in joules? All right? Remember, same direction, positive work, opposite direction, negative work, perpendicular, no work at all. Hope that helps. I'll put this on Schoology. You guys should have this in a little bit.